This is number 59 in chapter 10. We need to determine if each pair of compounds forms a homogeneous solution when combined. For those that form homogeneous solutions, indicate the type of forces that are involved. And so we're just trying to figure out whether we have something that's homogeneous, and if it's not homogeneous, then it would be heterogeneous. And so it's really a question of forces. Homogeneous, you would have the same types of forces of attraction, while with heterogeneous, you're going to find that these are going to be different forces present in the two molecules. And so let's look at part A. Part A looks at carbon tetrachloride and H2O, and whether we're going to get a homogeneous or heterogeneous solution. If we draw these molecules, we need to do that in order to discern whether they have the same type of force or not. In this case, these are both tetrahedral electronic geometries. In the case of carbon tetrachloride, though, these bond dipoles all cancel out, and so we're left with dispersion forces. As a result, with water is our best example of hydrogen bonding, and so we see a drastic difference in our forces, and so that's why we would get a heterogeneous solution. We would not get mixing of these two molecules because of their drastic difference in their forces of attraction. Part B looks at potassium chloride and H2O, and if we analyze their forces, we have potassium chloride, which would be ionic. We have H2O, which again, hopefully we know that this is a great example of hydrogen bonding. And when we mix these, we do get a homogeneous solution, even though we have different forces of attraction, ionic and hydrogen bonding. And that's because when we dissolve the potassium chloride, a new type of force results, and this type of force is known as ion dipole forces of attraction. And so what we see is that the delta minus of the water completely surrounds the positive cation of potassium. And so that is the ion dipole. We have the ion potassium interacting with the dipole of water, and that water completely surrounds that potassium, and that is why we get a homogeneous solution. We also see the same effect with the other charged element, in this case the anionic chlorine. And so we just have a reorganization of the dipole, and so in this case we have the delta plus portion of H2O surrounding the negative chlorine, and so we end up with those same types of ion dipole attractive forces, which create the homogeneous solution. So that's why a lot of ionic compounds actually dissolve in water, because when they dissolve, they create this new type of force of attraction, which is referred to as ion dipole forces. Okay, so part C is then looking at bromine versus carbon tetrachloride again. Bromine has no molecular dipole. Carbon tetrachloride also does not have a molecular dipole. So both of these have dispersion forces, and that's why it's going to be homogeneous, because they both share the same type of force of attraction, namely dispersion forces. And so that's when we would get then also a homogeneous solution, again, if we have the same type of force of attraction. And part D, the last example, is looking at CH3, CH2OH, and H2O. And so if we draw our structure, we have ethanol. And ethanol would look like this. And then we have water, which looks like this. And so we find that both of these guys are molecules that have hydrogen bonding as their force of attraction. And so as a result, we would also find a homogeneous solution with the force of attraction creating that homogeneous solution being hydrogen bonding. Again, if you have the same forces of attraction, you're going to create homogeneous solutions. If you have differing forces of attraction, you are going to create a heterogeneous solution. That is number 59.